All right, let's dive into one of the coolest parts of artificial intelligence, how it tackles massive, complicated problems. We're going to explore a set of tools known as local search algorithms.
So I want you to picture this. You're a climber standing in a massive mountain range, and your mission is to find the absolute highest peak. The only problem, the entire range is blanketed in a thick fog. You can only see a few feet in any direction. You can feel if your next step is uphill or downhill, but you have absolutely no map, no bird's eye view. This is the exact kind of challenge that AI faces all the time when it's trying to find the best possible solution to a problem.
In AI terms, this foggy landscape is what we call the problem space. Every single spot you could stand on is a possible solution, and its height, or elevation, tells you how good that solution is. Our goal is to find the highest peak in the whole range, the global maximum, which represents the perfect, optimal solution. So the big question is, what's our climber's strategy going to be?
Well, the strategy our climber uses is called local search. And honestly, the core idea is pretty straightforward. You just start somewhere, could be anywhere, and then you look at your immediate surroundings, your neighbors, and take a small step to a better spot. You keep doing that, improving your position step by step, hoping that a bunch of good little moves will eventually lead you to the very top.
Okay, so let's start with the most basic, most intuitive strategy in our climber's toolkit, the hill climbing algorithm. It's simple, it's fast, and it's probably what most of us would do if we were stuck in that fog.
The rule for hill climbing is dead simple. From where you are, just look around and take a step in whichever direction goes up the most. That's it. It's what we call a greedy approach because it's only focused on the immediate reward. It doesn't have a grand plan. It just wants to go up, up, up right now.
And here's exactly how that plays out. First, you just plop down at some random starting point. Second, you check out your neighbors, all the spots you can reach in one step. Third, if one of those spots is higher up, you move there. And then you just repeat the process. But what if none of your neighbors are higher? Well, then you must be on a peak, so you stop. Easy, right?
But as you've probably guessed, it's not always that easy. This simple, greedy strategy has some pretty serious blind spots. That fog we've been talking about is full of traps that can easily fool our climber.
That always go up rule sounds great, but what happens when the best uphill step in front of you doesn't lead to the main summit, but just to some smaller hill? This is where our simple climber can get into real trouble.
And this is trap number one, the most common one, the local maximum. Our climber reaches a peak. Every direction from here is downhill. So the algorithm stops and thinks, job done, but it's a false peak. The real highest mountain, the global maximum, is somewhere else entirely, and our climber is stuck with no idea that a much, much better solution even exists. The next trap is the plateau. Imagine our climber wanders onto a huge, perfectly flat area. Every possible step is at the exact same elevation. There's no uphill direction to follow. Our climber is completely lost, just wandering around this flat expanse with no clue how to make progress.
And finally, we've got the ridge. This one's pretty tricky. Think of a long, narrow crest. To get to the real summit, you might have to walk along the top of this ridge. But the hill climbing algorithm is short-sighted. It only looks one step to the side, and any single step off the ridge leads sharply downhill. So it gets stuck, refusing to move because it can't see the path forward along the ridgeline.
So yeah, our simple climber gets stuck. A lot. Clearly, we need some better gear. It's time to break out the advanced climbing toolkit and look at some smarter strategies for conquering these tough landscapes.
Instead of just one lonely climber, what if we sent out a whole team? That's the big idea behind local beam search. You start with a handful of climbers at different random spots. At each step, they all explore their neighbors, and then we check in and only keep the best climbers in the most promising spots. That way, if one climber gets stuck on a false peak, the others are still out there searching for better paths.
Now, this next one is really cool. It's called simulated annealing. With this strategy, the climber is sometimes allowed to make a bad move, to actually take a step downhill on purpose. Now, why on earth would you do that? Well, it's how you escape from those false peaks. At the start, the temperature is high, so the climber is kind of reckless, making big random jumps to explore widely. As the temperature cools, the climber gets more careful and starts to zero in on the best peak it's found.
All right, let's talk about our final and maybe most powerful tool. This one is inspired by the best problem solver we know, natural evolution. I'm talking about genetic algorithms.
We're not using one climber or even a small team anymore. We're about to unleash an entire population of solutions and let them evolve over generations to find the best one.
And what's so amazing here is how perfectly the concepts from biology map onto computing. In nature, you have a population of individuals. In the algorithm, that's just a set of possible solutions. An individual's fitness in nature is its ability to survive. In the algorithm, it's just a score for how good the solution is. It's a direct parallel all the way down to reproduction and mutation.
So here's how the cycle of evolution works. First, you create a random population of solutions. Then, you test them all out to see how fit they are. Next comes survival of the fittest. You select the best solutions to be the parents of the next generation. They combine their traits through crossover, and sometimes you throw in a random mutation just to shake things up. This creates a new and hopefully better generation. And you just keep repeating this cycle until you've evolved an amazing solution.
Crossover is really where the magic happens. The algorithm takes two strong parent solutions and literally combines their best features, their genetic code, to create a new offspring solution. The hope is that this new solution will inherit the best traits from both parents and be even better.
And you can do this in a few different ways. On the left, with single-point crossover, you just pick a spot, cut the two parent solutions, and swap the second halves. On the right, with two-point crossover, you're swapping the middle sections. Either way, the goal is the same. You're constantly mixing the DNA of your most successful solutions to drive the evolution toward an even better one.
Okay, so we've been talking about climbing mountains in evolution, which is a great way to understand the concepts. But how do these algorithms actually solve real, tangible AI problems? Let's bring this all back down to earth. Let's take the classic 8 queens puzzle. The goal is to place 8 queens on a chessboard so that none of them can attack each other. In our metaphor, the landscape is every single possible arrangement of those queens. The elevation of any arrangement is determined by how few queens are attacking each other. And the peak we're searching for, that's a board with 0 conflicts, the perfect solution.
And these algorithms are absolute workhorses for some of the most complex problems you can imagine. They're used to solve things like the knapsack problem, how to pack the most valuable items you can without going over a weight limit. They're crucial for the traveling salesman problem, finding the absolute shortest route for deliveries. We're talking about complex logistics, scheduling flights, you name it.
So in the end, what started as a really simple idea, just take small, good steps, blossoms into something incredibly powerful. By borrowing ideas from teamwork, from physics, and even from natural selection, these local search algorithms give AI an amazing toolkit to find clever solutions to problems that are just way too massive for us to solve on our own.
It really makes you wonder, doesn't it? We've already looked to geology and biology to build these amazing tools. What other complex, elegant process from the natural world is out there just waiting to inspire the next huge leap forward in artificial intelligence? It's a pretty exciting thing to think about.